হ্যালো প্রফেসর পাল, তোর এটা ইয়ে কর, মিউট কর, মানে অডিও জিরো করে দে, তাহলে হেডফোন গুঁজে দে। ফিডব্যাক হবে। হ্যালো স্যার, গুড ইভিনিং। হেডফোন গোজ, ওটা এখান থেকে নিয়ে যায়। হেডফোন নেই, ওইখান থেকে দেখ। Hello, madam.
Hello. Yes, you can hear you.
So we wait for another 2-3 minutes, and then after that we will start. So Minhaz, we will wait for another 2-3 minutes, and after that we will start.
Hello, am I audible?
Yes, audible.
Hello, Professor Pal, I can't hear you. Is it due to, okay, maybe my, hello?
Yes, sir, we can hear you.
Okay, thank you. Yeah, okay, thank you. So how should we go? Sir has come, or Sir will come, no?
Sir, Director sir is in the meeting. Professor Bhomik is here, and Professor Punika
Okay.
Das Bhattacharya is here.
Okay,
They will start the session.
Okay. So just please tell me when I start.
Yes, sir. Just within few minutes, let some other participants join also. Okay, good afternoon, everybody. There is some other meetings are going on, so honorable director will not be able to join here. Our president, Professor Bhomik, and vice president, Professor Konchalas Bhattacharya is here. So I will request our president, Professor Bhomik, to inaugurate the event. Esteemed faculty members of IIST Shibpur and my dear students, a very good evening to all of you. I, on behalf of Institution's Innovation Council, ED Cell, and PCGTBI of IIST Shibpur, welcome you all in today's webinar on the occasion of National Science Day. National Science Day is celebrated every year on 28th of February to commemorate the discovery of Raman Effect, a phenomenon of scattering of photons in 1928, for which Sir Chandrasekharan Venkataraman was awarded the Nobel Prize in 1930. And this was the first Nobel Prize for India in the field of science. Raman effect is a phenomenon in spectroscopy discovered by Sir C.V. Raman while working in the laboratory of the Indian Association for the Cultivation of Science, Kolkata. In 1954, he was honored with India's highest civilian award, the Bharat Ratna. Government of India designated 28th of February as National Science Day in the year of 1986. The basic objective of observations of National Science Day is to spread the message of importance of science and its application among the people. The theme of National Science Day 2022 is the integrated approach in science and technology for the sustainable development, for the sustainable future, for the survival of the humanity. Our initial planning was to organize this event, an open house for our laboratories, and appraise our students about the research facilities available in our institutions. But this could not be materialized due to the pandemic situations. However, at this juncture of time, we are observing how all the institutions, the government agencies, and the industries, they have come forward and work together to bring India and the world to overcome the challenge of the pandemic situations. In a nutshell, Raman effect is characterized by change in the wavelength of light that occurs when a light beam is deflected by the molecules. So, however, this statement is not sufficient to describe the vastness of this phenomenon. To elucidate this effect more elaborately, and with practical demonstration, we welcome our invited speaker, Dr. Syed Minhaz Hossain, Associate Professor and Head of the Department of Physics, IIEST Shibpur. Dr. Hossain received BSc and MSc degree in the year of 1994 and 1996 respectively. He obtained his PhD in the year of 2002 in physics from Jadavpur University. His research interest includes low-dimensional solid-state physics, photonics and photovoltaics in nanoscale, electronics, optoelectronics, and sensing applications of nanostructured silicon. Dr. Minhaz Hossain received Boy Scout Fellowship in the year of 2007 and Care Fellowship in the year of 2012. He is a life member of Indian Association for Cultivation of Science and Indian Association of Physics Teachers. He has published more than 50 papers in reputed journals and proceedings. So let us welcome Dr. Minhaz Hossain, and we are waiting to hear his talk. And the good thing is of today's webinar that he will also demonstrate some experiments on this particular topic. Thank you.
Good evening, everyone. My dear faculty members, my colleagues, and my dear students. Thank you, Professor Bhomik, for your nice introduction. I'll not actually talk about Raman effect today, but I'll talk about scattering. Raman scattering. Instead of Raman scattering, I'll show different types of scattering that we see in our atmosphere. Mainly, that's why the name I gave, the topic of my today's talk and demonstration is colors in the sky. So let me present my slides first. I guess my slides are visible. I need a feedback. Is it fine? It's okay? Can you see my slides?
Yes, sir. Yes.
Okay, thank you. So, if we look at the sky, normally what we see a blue sky and white clouds moving around. Sometimes before the monsoon or when monsoon is going, autumn is coming, at that time, sometimes we see halo, rainbow, and every day when the sun is rising or it's setting down, we see a nice red sun in the horizon. And if we have a nice weather, less pollution, we see a nice blue sky. So today I'll discuss about this. This talk is mainly for aimed at senior school students and first year undergraduate students of science and technology. So let me start with cloud. What is cloud? We all know that cloud is a visible mass of water droplets or frozen ice crystals suspended in the atmosphere above the surface of the earth. Depending upon the atmospheric condition, the temperature, the moisture content, all these things, The content of ice and water vapor, it depends. Depending upon pollution, the dust particle and suspended particle content also depends on different things. And depending upon that, the color of the cloud varies. Now I'll show you how we can, just let me start from a demonstration. So we know cloud is a collection of suspended water molecules. They are condensed on dust particles mainly. Dust particles in the atmosphere, it works as the nucleation center for condensation, and that gives you, cloud. So let me create cloud in this laboratory. Okay, just during this demonstration, I want to show you how cloud can be formed in the laboratory within a bottle. What we need for that, we need switch off the light, and we need a bottle, plastic bottle, water, a piece of paper or a resin stick will also do, a matchbox with stick or a lighter for fire. I need to lit the piece of paper for this purpose. And let me demonstrate how I can generate water in a... Okay, can you switch on the light first? I have to show these things first. Then. So I have here is, can you see the bottle? So here is a bottle containing a bit of water. Okay. So what I am doing, I'm pressing it and releasing. We don't see any difference. Okay. Now I'm doing one more thing. I'm just lighting a piece of paper and putting it inside. Let me do one thing. Let me pin the camera. Yes. So here is the bottle. And what I am doing, I'm taking a piece of paper and then I'm putting this fire inside the bottle. And I'm closing it. Now can you see this? I'm pressing it and releasing it. When I'm pressing, it is almost transparent. Look at this, it is almost transparent. I'm releasing it. It's totally hazy. Now I'm again pressing it, it's clear. Then releasing, it is hazy. Haze is created inside the bottle. Again I'm doing it. Clear, and then it's full of haze. It will be clear, it will be clearly visible if I switch off the light and I am putting it in front of a black carton. So can you see that? Can you see the cloud coming out of the bottle? So this is a cloud generated within a bottle. And note the color of this cloud. This is whitish, gray. Okay. So now let me explain why this happens. Again, let me come back to my presentation. Now to explain this, it's for school students. So we all remember that dq is equal to du plus dw. For adiabatic process, I'm pressing the bottle suddenly and releasing it suddenly. So there is no time given to transfer the heat. Okay, so it's an adiabatic process. So our dq equal to 0 in this case, no transfer of heat energy from water to outside environment. So du is equal to minus dw, and the work done dw is minus PdV. So dU equal to minus PdV. Now when I'm pressing it, dV is negative. So du is positive. So that means the internal energy of the water molecules inside the vapor molecules increases. That's why the internal energy increases means the kinetic energy increases. So the particles, they move away from each other. So they become, they vaporize. Okay. And when I'm releasing suddenly, what happens? The opposite process is taking place. So the internal energy decreases and the kinetic energy decreases. So they freeze. Okay. I mean, they condense on the, where they condense? Actually, you probably you noted that when I did the same process, pressing the bottle and releasing without putting a piece of paper, I lit the piece of paper and put it inside. I just did that to create some soot particles, dust particles, because I told you that cloud is created due to condensation on dust particles. Okay, so I need some kind of macroscopic, little bit larger particles on which the condensation can take place, and the soot particle actually plays that role. So that's why I put light inside, a piece of burning piece of paper inside, and then I did this adiabatic process, and this cloud is generated. I'll come back to this thing again after some time, and let me switch to the next phenomena. Sky is blue. We all know that in a clear sunny day, we can see blue sky. And we all perhaps know that this is due to scattering of light. Okay. So what is scattering of light? In any molecule or atom, it's a collection of positive and negative charges. So when electromagnetic wave falls on that molecule, which is a collection of neutral collection of positive and negative charges, normally the total amount of negative and positive charges are same. Not only that, the center of positive and negative charges, they fall on each other. So we don't get it as a charged particle. We see it as a neutral particle. But when electromagnetic wave falls on that atom or molecule, electromagnetic wave has got electric and magnetic fields which are oscillating sinusoidally. So what happens? The positive and negative charges, they fill the electric field, and it's a forced vibration. It is called dipole. Because the positive charge moves towards the field and the negative charge moves away from the field. So the electric field will oscillate and giving rise to an oscillation of the dipolar oscillation of the molecule or the atom. Now that generates secondary electromagnetic wave, because perhaps we all know that when we have charged particle oscillating or accelerating, then we have electromagnetic radiation everywhere. So the light that was moving in this direction is now scattered in all the possible directions, because the oscillation is taking in in this vertical direction. Okay, in this vertical direction, the oscillation is taking place. So light can be emitted in all the perpendicular directions. So in all possible directions, it is scattered. So this is the phenomena of scattering. Now, how this scattering actually leads to blue color of sky. We know that if the wavelength of light is much, much greater than the scatterer, the dipole, then what happens? The formula that gives the dependence of how much scattering will take place, the dependence of the scattering cross-section on the wavelength is given by Rayleigh scattering formula, which gives you I is of the order of 1 over lambda to the power 4. That means if the wavelength increases, the scattering cross-section decreases. So in the visible region, if we start from violet to red, violet gets maximum scattered and red gets minimum scattered within the visible region. So it's something like this. We have a white light containing all the possible violet to red colors. The scattering of violet is maximum. The scattering of red is minimum. So to explain this color of the sky, we should understand that when we are looking at the sky, we are not looking at any direct source of light. We are not looking at the sun. we are looking at the sky that contains different molecules, atoms, and particles, different kind of scatterers. Now, light is falling on those scatterers, and light gets scattered and coming to our eyes. So, sunlight gets scattered by the molecules and atoms and suspended particles. Scattered light comes to our eyes, and color of the sky is the color of the most scattered light. Now, which color is scattered the most? Let us perform an experiment. We know from Rayleigh's formula that it is 1 over lambda to the power 4. So violet should be scattered the most. I have in my laboratory, I have a laser torch of 405 nanometer wavelength. It's a kind of blue UV, violet UV kind of 405. So just in the boundary of visible light, it's a violet light. And let me show you an experiment. Put the camera on that water. Okay, so let me do one thing. Let me introduce my students who are helping me out in this demonstration. I have my PhD student, Shairi Basu. Here you see, this is Shairi, and here is Shudipta, and there is Shubhajit, who is controlling the light. Okay, so let me show you how scattering depends on the color of the light. Okay, so is it there focused? Focus there. So this is red light, right? So you can see I'm putting red laser here. Okay, when I'm putting the laser above the water in air, you don't see any light. You don't see any light. Here, you can understand that. You can understand that I have light is passing there. Okay, but we don't see anything here. Why? Okay, we don't see anything. Why it is so? Because we have some dust particle definitely there, but when we are putting in water, water has got much more scatterer, suspended particles and all these things. So, okay, let me do one. Thank you. Let me pin the camera. Yes, you can see the scattered light, right? You can see the scattered light. Light is getting scattered through the water molecules, okay, and other particles are definitely. So, so what is my point? The point is, I am putting the laser in this direction, okay, which is perpendicular. You don't see anything, but when I am putting it in water, you can see from the perpendicular direction of the direction of propagation. Here it is. So this is the scattered red light. Now you will be able to compare if I put violet light. So whose intensity is higher? So this is the second one is the violet one. Okay, this is the second one. So the violet light is scattered much more heavily. Okay, so this is a simple demonstration that tells you that blue light gets much more scattered than red light. Okay. Now I'll come back to my slides again. So why? So we understand that violet is most scattered and red is not. Now, why the sky is not violet then? Why we see a blue sky, not a violet sky? So the answer lies in two facts. One is the solar. If we look at the solar spectrum, the spectrum that comes to Earth's surface does not contain, the intensity of violet light is much lesser than that of blue light. That is one point. The other point is our human eye response is maximum towards the green yellow region. So if you have same amount of violet and blue, then we'll see it a little bit bluish. Okay, so that is due to the even if you have violet and blue of same intensity, we'll see it's bluer. And the fact is, in solar spectrum, we don't have the same amount of violet and blue. We have lesser amount of violet than blue. So blue is the most prominent color that comes to our eyes after scattering. That's why we don't see a violet sky but a blue sky. Now, setting and rising sun is the color of the setting and rising sun is crimson red. Why it is so? The reason is the same. When sun sets or rises, it goes, the sun is very close to the horizon. So what happens? The distance traveled through the atmosphere in comparison to the mid-noon when the sun is at the top, it just directly comes to Earth's surface. The distance traveled by the light particles, photon or light, whatever, is much more lesser than the situation when we have a rising sun or a setting sun. Okay, so due to this, what happens? The light, it's near to horizon, so it bends, light bends due to refraction, and we actually see the sun a little bit in an elevated position. But still, the distance traveled is much higher than the distance that is traveled by the light coming directly from the sun when it is at the top. So that leads to thickness, optical thickness traveled by the light is higher, so that leads to higher number of scatterers in the sky. Okay, so if you have more scattered particle, then what happens? You'll have blue light more scattered and red light less scattered in comparison with blue and lower wavelength lights. Okay, so that's why we'll see a crimson reddish sun when it is close to the horizon. That means during sunset or sunrise. So let me demonstrate this by using a simple experimental setup. For this purpose, I need a glass box, a light source that will act act as the sun, the source of light. I'll use sulfuric acid and sodium thiosulfate and a plastic straw to start the solution, such that sodium thiosulfate, after reacting with sulfuric acid, creates sulfur. The equation is given here. The sulfur particles will act as the scatterer. Okay, so let us see what happens. Again, let me put my video the pin position. I'm doing. Okay, so switch on. Switch on the light now. Now it's not needed. Okay. So here is my source of light, a torch. Okay, this is the torch. So this is the source of light. I have to put it a little bit down. It's fine. And here is water. And where is the sulfuric acid? This one. So this is the sulfuric acid. I'm adding 20 ml of sulfuric acid. And then I'm stirring it. And after that, what I'm going to do, I'm going to add sodium thiosulfate. Now, Shubhajit, please switch off the light. So here, what happens? Look at the bluish tint, already it has come because I have some scatterer already there. So look at the water, light passing through water. So this is a set of cylindrical scatterer, I mean cylindrical region of scatterer. So this is my sky. Okay, sky for this experiment is basically a collection of scatterers. Okay, which is here the cylindrical region that we can see, and that is the sun. Move the camera towards the screen. So this is the sun. That means the image of the torch on a white screen. So sunlight, which is our torch, coming through the sky, which is the sulfuric acid and water mixture, and then so this is my sky, and then the sun that we see is the image of the torch which is falling on the screen. So now I am adding the sodium thiosulfate. Okay. So I'm starting it, and let us see what happens. So look at the focus on the sun. So it has already started becoming yellow. So it is white, so all kind of wavelength is there. Now it is becoming a little bit of yellowish. There is a problem in online thing because the camera, it has got its own spectral response. Sometimes it doesn't give you exactly what we see offline. It's a bit yellowish now, but the camera is got saturated, so probably that's why it is not that much yellow. So can you give me a piece of tissue paper? I'll reduce the intensity. So it will take some time because sulfur it is becoming a little bit bluish also. The sky is also becoming a little bit bluish. Let me decrease the intensity. No, it will not be possible. Now give me the camera. Look at the sky. Sky has become blue now. Okay, can you see this blue sky? The scatterer. So number of scatterer with time, more and more sulfur is being deposited. So number of scatterer is increasing, and I can see a blue sky. It will become more and more blue. It is now more blue. It will take some more time, I guess, for the sun to become red. Let me add some more sulfur. No. Well, now the intensity is decreasing because of the scatterer, and you can see that the sky is no more blue, it has become more and more white. You almost don't see a blue sky, you see a white sky. Why is so? Because this is due to the same reason why the cloud is white, not blue. Now look at the sun. It's to us, it's clearly red, but due to the camera, it's becoming saturated. Let me go a little bit away. Still, it is. I guess you can understand that it's becoming red. The central region is still white in the camera, but we can see with naked eyes it's really red. Yeah, now you can see that this has become almost red. It's like setting sun. So here you can see in the bottom, in the glass tank, a white sky. That means a sky full of cloud, and the sun is now it's red. In the camera also it's red. Okay, so it's fully red now, I guess. It depends on the spectrum of the detector of the camera also. It is tuned towards in such a way that it gets saturated. The intensity is a little bit higher. But now you can see a really red sun. So here we have initially a blue sky which has become whitish, and a red sun in the horizon. Okay. So let me switch to my next demonstration. Now, let me ask this question. Sky is blue, but cloud is white. And we have seen it experimentally that when we have a lot of sulfur particles suspended in water, the bluish tint of the medium has become whitish. Why it is so? This is because that in Rayleigh scattering we assume that the particle size, the scatterer size, is much smaller than the wavelength of light that is being scattered. So the formula becomes like 1 over lambda to the power 4. Okay, if you look at this formula, it becomes like 1 over lambda to the power 4, and it's this d over lambda, d over lambda. This d term is basically much smaller than lambda, so it becomes almost independent of particle size. D independent. Let us look at the graph I have shown here. But the Rayleigh scattering is not the only theory of scattering. It has got this approximation that our lambda is much smaller than the. Okay, so what happens? Just look at this curve. The scattering cross section versus this particle size is something like this. Okay, so if we have larger particle size, what happens? It becomes almost independent of particle size. So this is the region, Rayleigh region, somewhere here, where particle size is much smaller. And if we go to larger particles, the scattering cross section becomes almost independent of particle size. So in that case, what happens? Independent of lambda, for that matter. So for a given particle size, this region becomes independent of lambda. So if we have independent of lambda scattering cross section, then what happens? Blue light will be more scattered and red light will be less scattered. This will not be true in general. So what happens when we have larger particles we have almost all the light component inside white light will get scattered in the same fashion. So the mixing of all the lights will again give you white light. That's why if we have smaller particles like molecules, then we see blue sky. But when we have water particles, that is on the dust particles, and it gives you, we get cloud. So it's larger particles, gives you Mie scattering, not the Rayleigh scattering, and Mie scattering gives you almost wavelength independent scattering cross section. So we get white light. So let me demonstrate this fact also. Why? The difference between Rayleigh and Mie scattering can be easily seen, demonstrated by a simple experiment. What I do, I take a resin stick, a dhupkati, okay? A resin stick, I lead the resin stick, and it contains large number of soot particles. The smoke that comes from the resin stick is basically carbon particles, soot particles. So we see this switch off the light and focus there on the black screen. So you can see the smoke that is coming out of this resin stick has got a bluish tint. Okay. Now what I need to do, I'll just put this smoke inside my bottle. Okay, that which I use to create cloud. So I'm putting, switch on the light and put the camera, focus the camera in this direction. Yeah. So I'm putting this resin stick inside my bottle such that I get a lot of smoke inside the bottle. The same blue smoke I'm putting inside. Open the light. Yeah. Okay, what I'm doing. Let me pin the camera. So I'm putting smoke inside this bottle. Okay, sufficient amount of smoke is there. So the same bluish smoke I'm putting inside the bottle. Now I'm mixing it with the water inside. So switch off the light and let us look at the smoke. It is no more blue. Look, it is just like cloud. So you can see whitish color. So the blue smoke has turned white. Okay, so blue sky full of cloud becomes white. Why?
Okay, we are experiencing technical difficulty.
Hello. Hi
Yes,
everyone.
sir. Yes, sir. You
Yeah.
are
Am
audible.
I audible now?
Yes,
Yeah,
sir.
my connection got lost. I
Yes.
got Wi-Fi connection from mobile and then. Yeah. Okay, so let me present my slides again. So I guess I could show you only the bluish tint of resin smoke. The second part of this experiment, before that the connection was lost, I guess. So can somebody give feedback?
Yes, sir. Yes.
Yeah. So I'm showing that experiment again. So let me fix it here. No, that resin and bottle. Yeah. So here is the bottle. Let me pin here. Is it pinned? Yes, it's pinned. Give me the resin stick. Yeah. So what I have a bottle of water, and then I'm putting the resin stick, which is burning. So it's creating smoke, which is for our purpose. It's providing us scatterer. I mean, soot particles, carbon particles. Okay. So I'm putting a lot of smoke inside. Okay, so this will be sufficient, I guess. Can you hold it? Yeah. Okay. So I am mixing this smoke with water. Okay. So what I'm expecting is, show the camera there. Yeah. That the color of the smoke will be turned a little bit whitish. So it is no more bluish, it is whitish. Okay, so can you give me the resin stick again for comparison? If you see, it is much more bluish. That is bluish, but when I put this resin smoke inside bottle containing water, the vapor becomes white. White is so because as a physics student, we can understand that we are switching from the Rayleigh regime to me regime, where blue light is not more getting scattered, but at the same time, all other lights are also getting scattered with similar scattering cross section. So why it is? Because we have soot particles and we have water vapor inside. So water vapor is getting condensed on the soot particles, giving those larger particle size, and we are moving from Rayleigh to me scattering region. Okay, let me again present my last two parts of this presentation. Normally what happens when we are in the beginning of monsoon during May, June month, or during September, end of August or September middle, we see this kind of things. In Bengali it is called Shobha, Chander Shobha, Surjer Shobha, but in English it is called halo. So this part, a nice ring around the source, sun or the moon, we see this kind of optical phenomena. This is called a 22-degree halo. Why it is so? Let me explain this. Actually, perhaps you know that this phenomena takes place due to presence of ice crystals in cloud. That's why we need, starting or ending of monsoon, when we have cirrus cloud. Cirrus cloud is a little bit of a higher altitude cloud where we have lower temperature. So not only water vapor, we have ice crystals in the cloud. And our ice crystals are normally hexagonal in shape. So that can be considered as a prism. So just before going to details of ice crystal, just to recapitulate, let us consider a prism. prism has got the prism angle A, the incident angle I1, and the deviation delta. This is the deviation delta. Now this is our delta 1. Delta can be, here what happens, we have this amount of deviation in this first incidence. So this is I1 minus R1. Then here we have again deviation I2 minus R2. So this is I1 plus I2 plus minus R1 plus R2. This is school stuff. So we get an expression for delta, the deviation of light when incident on a prism is I1 plus I2 minus A. This is standard textbook problem of school students, senior school students, higher secondary students. And we also know Snell's law. So clubbing these two things together, we can get an expression for delta as a function of incident angle I. If we plot this curve, we get a curve which has got a minima here. And this is called I delta curve that shows a minimum deviation region. That means if your incidence angle is this much, you see minimum delta. If you have lower incidence angle, then also you will have larger delta. And if you have higher incidence angle, then also you will have higher deviation of the light after incident on the prism. So the expression for this minimum delta was also during our time, this was a nice, standard question in higher secondary, relation between delta M and prism angle and refractive index. That is this expression. Now let me do one thing. I'll not show this experiment here because it will take time. So it's an easy thing. I'll not show that. So let us consider an ice crystal. Ice crystals are something like this, which are in cloud. Now you can consider this ice crystal as a hexagonal prism. So ice crystal is a natural prism, and it comes in atmosphere like flakes. So a cross section of ice crystal is something like this, a hexagonal piece of structure, solid structure. And there are a few options. If light falls on this surface, and if we consider this as a prism, then light comes out from this surface. Okay. Similarly, in this case, this angle is 120 degree. A is 120 degree. Now, if we consider this cross section like this, such that the light is incident on this surface, then what we get? We get a prism of prism angle 60 degree. And there is one more option. When light falls on this vertical surface and comes out from the horizontal surface, it is something like a prism with this angle. This is the angle. Okay, so it is something like this. This is the prism. So this angle is 90 degree. So prism angle A is 90 degree. So in option 1, A is 120 degree. So if we plug in the formula for refractive index and A and delta M, what we see? We see delta M is equal to 2 sine inverse this guy n sine A by 2 minus A. Now if you plug in the value of refractive index, what happens? Refractive index for ice is 1.31. If you plug in this, then theta C is 50 degree. And we have found that this for refraction through prism, the condition is A must be less than or equal to twice theta C. Now theta C is 50 degree, but A is 120 degree. So this is more than, this is definitely, the A that we have actually is 120 degree, which is more than this 100 degree. That means what happens? It will not be reflected. Refraction will not take place, but this thing will happen. That means total internal reflection will take place. So when light incidents on this surface, it will not be reflected, it will come back inside the prism through total internal reflection. So that option is gone. So A is equal to 120 degree is no more there. That will not serve our purpose of explaining halo. Now in option 2, we have A equal to 160 degree, and we understand that this is less than 100 degrees, degree. So it will give us this kind of refraction, and n is equal to 1.31 gives us delta m is equal to 22 degree. Okay, so delta m, the minimum deviation through this prism, when the prism angle is 60 degree, we get a minimum deviation angle of 22 degree. And what about option 3? In option 3, A is equal to 90 degree. So this is also less than 100 degree, and delta m is equal to 46 degree. Okay. So what happens if we look at the I delta curve? Now, if you look at the I delta curve, if we are near this minimum delta point, look at this nature of the curve. This curve is much more flatter in this region. Flatter means if you change a bit of I, a lot of change in I will lead to very little change in delta m. Okay, so that means incidence angle changes a lot, but the delta m changes very less. Okay, so it gives you the actually color pattern of halo. That means d delta di near this region, the minimum region, is 0. So almost delta is not changing if you are close to the minimum deviation position. Now what happens when halo is formed? We have the source of light, sun or moon, which are falling on ice crystal, and the light that is source is at very far distance. So light is nearly parallel. So what we have falling ice crystals, and light is falling on those ice crystals, and they're acting as prism of A is equal to 60 degree. So they will be deviated by an angle of 22 degree. And as a result, we'll see light at an angle of 22 degree, which is the halo. Now, there are two options. If the light falls on the second surface, then we'll see 22 degree halo. And if the light falls on the kind of vertical surface, then we expect to see 46 degree halo. Okay. Now, let us try to understand this thing. What will we see? 22 degree or 46 degree? So if you perform an experiment with falling body, what happens? If you have this kind of structure, rectangular parallelepiped, which direction is most likely to be oriented? You understand that in this direction, the air drag will be more. So this is less likely, this is more likely, and definitely we have a kind of air resistance, viscous medium. So it will try to get minimum viscosity, and this is the most preferred orientation. So the ice crystals which are falling will be something like this, making the surface like, it should fall on such a surface that the light falls on the horizontal surface. So when this actually, if we have falling ice crystals and the elevation of sun is between 30 degree and 70 degree, then what happens? Light falls, the probability of falling sunlight on this surface is the most, and we get light deviated by an angle of 22 degree. So this is the 22 degree deviation, and as a result, but when we have 10 to 20 degree inclination of sun or moon, we expect to get 46 degree halo, because the ice is falling in this direction and sun is there, so there is a chance that light falls on this flat surface. Okay, so that gives us A is equal to 90 degree, and this gives us A is equal to 60 degree, leading to 22 degree deviation, and A equal to 90 degree will lead to 60 degree deviation. 22 degree, 46 degree deviation. Okay. Now let us look at the color of the halo. it's a prism, so the deviation will be from V to R. Okay, so deviation takes place in this direction. So V to R means the inner side, if we extend, we see halo in this direction. So the outer side will be V and the inner side will be red. Okay, and let us verify this image. Look at this. The outer side is almost white and the inner side is reddish. Why it is so? Because this is the minimum deviation. So the deviation is there, which is more than 22 degree. So here violet will be deviated, but at the same time red, blue, green, all lights will be deviated. So the outer side, in the outer side, there will be a mixing of all the visible lights leading to whitish color. But inside the circle, inside the halo, the inner edge, we see only red, because this minimum deviation will not be there for the other values, other wavelengths. So that's why the inner side will be reddish, but the outer side will be not violet, but whitish, because red can also make that deviation. So this is a nice picture of 22 degree sun halo. And there is one thing we don't see in Kolkata or in our region, which is called sun dog. Sun dog means in winter season, in higher altitude, like in Alaska or in Siberia, or in higher altitudes above 50 degree latitude, higher latitude rather, where we have falling ice crystals. You have falling ice crystals, and the ice crystals are falling vertically. The hexagonal crystals are falling vertically. So there is an orientation of the ice crystals, preferred orientation, which is falling vertically. Then what happens? We see this is the image of the sun. This is sun, and this angle is 22 degree. So at an angle of 22 degree on the left and at an angle of 22 degree on the right, we see two images of the sun, whose inner side is reddish and outer side is whitish. The same thing. So this sun is coupled with two more images. That's why these are called the dogs of the sun. So this is why it is called sun dog. Similarly, one more thing you can see, which is a kind of a smiley in the sky. It is sometimes called this Circum Horizontal Arc, or sometimes it is also a little bit variation of this is called Circum Zenithal Arc. This photograph was clicked by one of my PhD students, Sudipta, in Kolkata, in Howrah rather, from this very close, a place very close to our campus. It looks very much like a rainbow, but look at the arc. The arc is nearly horizontal and little bit of upward curve is there. If you look at rainbow has got the opposite curvature. So this is not due to the same reason as we see rainbow. This is due to this ice crystals. So let me show how these halos are formed. Let me demonstrate here in the laboratory. Okay. So what we need a hexagonal glass container that will act as my hexagonal prism of ice. What I'll put water inside that container and white light source that will act as my sun, and a screen where I'll show you the image. Okay, so let me focus on clean the camera. So here is the source of light. Now I have a container, hexagonal glass container. Okay, look at the hexagonal surface, hexagonal cross section, and this is actually mimicking ice crystal. So just there will be a difference because ice crystal has got refractive index of 1.31, but here it will be close to 1.33. Water is 1.3, so it is like that. So you can see the sun dog here. Okay.
It's getting saturated. So it's on the better, I think. No, not this one.
The distance.
Yeah.
No, take it from this side.
Color is not.
No?
Color is not.
The camera is getting saturated by the light. This is the problem. Oh, ये दिखलाम तो. Diffuser. Okay. Yes. Now they can see. Light up. Yes. No, light off full light of variance. So here you can see the central part is the image of the hexagonal prism, and it is accompanied by two sundogs. Okay, one is in the left, the other one is in the right. So this is just with single ice crystal. Okay, I mean single hexagonal crystal. You can see a 22-degree halo there. Actually, if we get proper light condition, and actually in offline, you can we will be able to see the 46-degree halo also. Yes, now it's much better. So we can't see the in offline. We can see the color variation also, but in camera it is not that much prominent. But we can see the 22-degree images of the light source. Actually, this is just mimicking the sundog. Now, sundog gives you just two images, but instead of one particular orientation, if we have all possible orientations from horizontal 45-degree or say 30-degree, 60-degree, 90-degree, all possible orientations are there for the ice crystal which are falling. Then instead of just two sundogs, we'll see all possible sundogs in all possible directions. That means we'll see a circular pattern. Okay, so this is here we can see only okay, let me go there. Okay. So here, what happens? Here we can see this is the source, and here we have one sundog, the other one is there. Now, if this prism is rotated by 90 degree, then what happens? We'll see a sundog here at the top and at the bottom. Similarly, if you rotate by 45 degree, we'll see one dog here, another dog there. Okay, so if we have all possible orientations of the ice crystal, then we have a circular distribution of the sundogs. That is actually the 22-degree halo. So here what happens? We don't have falling ice crystal. That's why we don't see kind of sundog here, because falling ice crystal means you have to go to a region where snowfall takes place. So here in the top high altitude, we have randomly moving ice crystals in form of cloud in the cirrus cloud region, and we see 22-degree halo when light passes through those ice crystals. So that's on halo, and the last topic of my demonstration is rainbow. Now, the last
Excuse me,
topic.
sir.
Yes, please.
Sir, you told that rotating the prism by 90 degree, we will have two more sundogs, upper and lower. How is the phenomenon done here?
Just rotate the whole setup by 90 degree. So instead of one ice crystal, if we have millions of ice crystal, one is vertical, the other one is kind of horizontal, another one is making an angle of 45 degree, the other one is 30 degree in all possible directions. So I have shown you the sun dogs by using one, ice crystal which is vertical, right? Now, if you have the ice crystal which is horizontal like this, then you will see the sun dogs in these 2 points. One is at the bottom, the other one at the top.
Oh, yes, sir. Yeah.
Okay. Similarly, if you rotate all these possible directions, video. Where is the video? Okay, let me see. No, video is there.
Maybe due to network.
Again.
No.
Can you see me? Is my video on?
Yes, sir.
Okay. Yeah. So you can understand that if you rotate the ice crystal in all possible directions, we'll have the sundogs in all possible directions, right? So there is a circular symmetry because 0 to 90 degree all in all the directions you are rotating. Okay. 0 to 180 degree rather. For one vertical direction, you get two sundogs. So if you rotate in all possible directions, you'll just get all the possible sundogs. So that will give you a circular image of the halo that we see.
Okay, sir.
So now let me switch to my last demonstration, which is a rainbow. Before that, let me, So here is an image of spectacular spectrum, which is a rainbow. Let me start with a question. I'll set up 10 questions. When do we see a rainbow? Where do we see rainbow? How many colors are there in rainbow? What is the angular radius of a rainbow? What is the angular width of a rainbow? What is the order of color in rainbow? How many bows are seen? 1, 2, 3, 4. If there are more than one bow, then what is the order of color? Is it the same in all possible, all the bows? And what is the angular separation between the bows if we have more than one bow? And the 10th question is, can two persons see the same rainbow? So is there any answer to these questions? Anyone in the class? When do we see rainbow? It's easy. When light falls on water droplets. Okay, so if you look at the image, you'll see that it's actually rain. Okay, when you have rain supplying the water droplets, and you have the source of light, that means the sun. So you have to have both together. In our childhood, we used to say, "Rodh hocche, biye hocche, rodh hocche, brishti hocche, kakshiyaler biye hocche." So it's something like that. So you have to have rain as well as sun together. Okay, in that situation, you can see rainbow. Rainbow can appear at that time. So where do we see the rainbow? It's opposite the sun. Let us have a look at this image. So here is the bow, look at this, the photographer. Here is a photographer. So this is the hat of the photographer. The shadow of the photographer is there. So that means the sun is behind the photographer. Okay. So you have the observer somewhere here. At the back, you have the sun, and then in front, you have the rainbow. Now, what is the angular radius? To give answer to this question, we have to perform some little bit calculations. Let us consider a single water droplet. Okay, so water droplet is a spherical one, and parallel rays coming from the sun is falling on the water droplet. So this is a typical direction of sun ray. It is falling on the first surface, then a part gets reflected, another part gets transmitted with refraction. Again, one part gets refracted, transmitted to the second surface, and it comes to the for another reflection goes inside, and another fraction comes outside of the droplet. So one transmission, one reflection, one transmission. So after these three optical phenomena, the light comes to the observer from the sun when scattered by this water droplet. So in this case, if I call this angle as delta 1, the deviation, to calculate this, we can understand that here, how much is the deviation? This is the angle of incidence I, this is R, so this much deviation takes place, which is I minus R. Here we have a reflection. So reflection gives you pi minus twice R kind of deviation. And in this surface, it is I minus R. So the total deviation of this angle, delta 1, is pi minus 4R minus twice I. Simple calculation. So this delta is basically the angle between the original direction of light, and if you extend in the opposite direction, light in the path of light, then this delta is basically pi minus this delta 1, that is 4R minus twice I. So this is the expression for deviation when light falls on water droplet. So angular deviation is this thing. Now couple this expression with Snell's law. Sin I over sin R equal to mu. Mu is the refractive index of water in this case. And here we'll see that if we plot delta versus I and use Snell's law to replace R by I, then we get an expression like this. I mean, a variation of delta like this. It increases, reaches a maxima, and then comes down. Okay. So for each refractive index, we'll get a delta max, the maximum deviation that a light can, can be, deviated when falling on spherical water droplet. So the maximum deviation condition can be found out by doing simple calculus. It gives you that the condition is cos I divided by cos R should be half mu, and Snell's law gives us sin I over sin R is equal to mu. So that gives a relation between I and R as a function of refractive index. I is mu square cos inverse mu square minus 1 divided by 3 whole root, and R is also 2 divided by mu square root of mu square minus 1 divided by 3. And delta max, if I plug in the values of R and I, we get this expression for delta max for a given value of mu. Now we know that water is a dispersive medium because refractive index of water is not constant for all wavelength of light, all frequencies of light. Actually, for violet light, refractive index of water is 1.345, and that for red is 1.331. So if we calculate the delta max for violet, that gives us 40.4 degree, and the deviation for red light is 42.4 degree. Okay. So what happens? Definitely, you can understand that during this refraction through the water droplet, there will be splitting of the color because it's a dispersive medium. Different light has got different velocity, so refractive index will be different, and they get splitted. Delta M for violet is 40.4, and delta M for red is 42.4. Okay. This gives you this kind of diagram that all lights are coming, white light is coming. So it's split in red and violet and all other intermediate colors, and it is coming. The red goes in the outside and violet goes inside. So if you extend, this pattern remains the same. Red goes outside and violet remains inside. So what we see as an observer, the observer is somewhere here. Observer is somewhere here. Here you have the sun, the source of light. Here is the observer, and we see the rainbow in this direction. So actually, it is a spherically symmetric object. So the pattern that we'll see is a circle with a red circle outside, a circular cross section, and violet circle inside, and intermediate all the colors. Okay, but actually what happens, this half of the rainbow goes below the horizon, so we don't see that. So we see half of the rainbow if we are kind of fortunate enough. But yeah, you'll be able to see the whole rainbow if you are flying on a plane and you are lucky enough that at that time you can see below the horizon, and this rainbow, the whole circle of the rainbow may be visible at that time. So inside the color cone, we have delta max is equal to 40.4 degree. So light of all color can make this deviation. Okay. This region is bright because this is for violet. If violet can make it, then all lights can make it. All wavelength can. This is because this is the maximum. Okay. So that's why what we see, this region should be bright because all lights will come here. So this will be whitish region. And outside the color cone, we have delta max is 42.4 degree. So only red can make this. So no light. So the outer region will be red and no light can make further deviation. So that is the maximum. So that region will be dark. Okay. So outside the rainbow, there will be dark region. And here you have the sun. This is the observer. And what do we expect then? If we have the water droplets somewhere here, then if you are looking at an angle of 42 degree, we'll see a violet light coming from these droplets. So violet light is coming from these droplets, red light is coming from these droplets, and intermediate, this is V, then indigo, blue, green, yellow, orange, all these colors will come. So in this region, actually we see the rainbow. Okay. Here in this region, we'll see the rainbow. Now below the rainbow, what happens? All the colors will come. So this region will be whitish, and above this region, we'll see a dark region because no color will come back to your eyes. The order of the color will be from outside, it will be red, inside it will be violet. So you can see this here. We have already mentioned. What is the angular radius? The average of the deviation can be taken as angular radius 42.4 plus 40.4 divided by 2. So 41.4 degree is the angular radius of the rainbow we are talking about. Now what is the angular width? The minimum is 40, the lower value is 40.4. The higher deviation is 42.4. So this is nearly 2 degree. So the width of the rainbow, if you measure the angle, it will be around 2 degree. You can perform this experiment when monsoon comes, maybe in the next May, June month. You can try. Secondary rainbow means I'm trying to give you the answer to the question, how many bows we can see. So here what happens? We have the other one. No. Yeah. So what happens again? When light comes and falls on the spherical droplet, it can take this kind of refraction and reflection. It goes there. One transmission, second reflection. Second point reflection, then one more reflection, then another transmission. So we can see it in this direction. So in higher altitude, higher elevation, we can see another rainbow. Okay. So in this case, if you perform similar calculations, you will see the deviation will be twice I minus 6R. So in this case, the condition of deviation will be like cos I over cos R equal to 1/3 mu. And follow the same calculations, you will see that for red, it is lower, 50.8 degree. And for violet, the deviation will be higher, 54.5 degree. So this makes the difference in order of color in the secondary bow. The angular radius of the secondary bow will be 52.6 and the width will be almost double the primary. The primary was 2 degree and this is 3.7 degree. The order of color, look at the order of color. In the primary one, outside you have red, inside you have violet. And look at the secondary one. Here we have inside we have red and outside we have violet. And this width is around 2 degree and this width is around 4 degree. Okay, this is larger. And this elevation, there is around 10 degree separation between the primary and the secondary rainbows. Okay, so look at this. We have the white region, bright region, the dark region, then the secondary one. Okay. Now, before I finish, let me show you a rainbow on the screen. Okay. For that purpose, what I have done, I have taken a round bottom flask here. Okay, let me pin the camera. Here is the round bottom flask. So this round part will act as my spherical water droplet, okay, with refractive index of 1.33. Okay, so this is a spherical droplet I will use. Okay, now I have a source of light. Here is the source of light. The mobile torch is acting as the source of light, and then we will switch off the. Little bit of, yeah. So can you see the rainbow? The outside is red, the inside is violet. Okay. So here lies the rainbow. You can make your own rainbow at home also. And if you want to perform experiments, like you can check whether this rainbow is polarized or not. So here is the rainbow. You can see the color pattern. Yeah, I hope these things would have been made offline because the camera has got its spectrum. That's why always the color is not that much prominent that we expect. Okay. So thank you. If you have any query, you can ask your question regarding these demonstrations. My protection is ulte geche.
Sir, is there a chance that the light gets polarized as
it's a good question. It's a good question. You know, whether light will get polarized or not, that depends on the angle of incidence. Okay, at which angle it falls, and depends on the refractive index. Actually, the angle at which we see the rainbow is very close to 98% polarization. So it will be a nice experiment if you see a rainbow, and if you have a Polaroid glass, sunglass, maybe you will miss it. You will not be able to see the rainbow because the Polaroid that you have in your glasses will cut it down. 90% will be cut down. So I didn't have time today. Otherwise, I could have shown you the polarization in rainbow. You can create your own rainbow and you can see how much it is polarized. I mean, it will not be possible to measure the percentage, but you will see that it's polarized. It's almost 100% polarized, 98%, as I said. Yes, it is polarized.
Okay, sir. Thank you, sir.
Yeah. So thank you for your attention. And I must thank my PhD students, Shudipta, Shairi, and Shubhajit, who helped me out by arranging this logistic support and all these. They helped me a lot in arranging these things. So thank you.
Thank you, sir. May I request Professor Punitala Bhattacharya, our Vice President, to give the vote of thanks.
Yeah. Okay. So thank you, Professor Minhaz, for this very demonstrative and interesting and lucid way of explaining to the students. Now, I just would like to say one line. Today is the day when the government of India has announced that integration of science with technology for a sustainable world. Now, what came to my mind after looking at his experiments was we have a subject, there is a thing called illumination, science and engineering. And there it came to my mind that fog lighting and even lighting in the dark, while if we go through the study of physics, whether you can develop more new types of light sources, keeping in tune with the behavior of the rays of light and the atmospheric particles, be it dust, be it ice, be it water, you can come up with new types of light sources which will be more energy efficient and more
network problem.
Experimental observations also. And we had a good science day to wind up with. Thank you, everyone, the students, and Tonmoy, and Dr. Shubhashish Bhomik, everybody, and director also, because he gave the approval at such a short notice. Thank you.
Thank you.
So we can now leave. Yeah. Okay. All right.